So there's this very common reduction that people have been concerned about, which is multi-class to binary classification. So that's the first thing I'm going to talk about. And, well, the next thing is cost-sensitive classification to classification. And the cool thing, I guess, about this is that it's so general as a classification problem that you can think of every classification sort of problem as cost-sensitive classification. But I'll get to that later. Okay, so multi-class classification is the same as binary classification, except we have more labels, right? So instead of predicting 0 or 1, you predict 1 through k. And your classifier is going to predict 1 through k. And then, given your multi-class data set, you want to find a multi-class classifier with a small error rate. So that means that, you know, the probability that you predict wrong from your D is small. And once again, I'm not going to be, throughout everything, I'm not assuming that these samples are actually drawn from D. It's not going to be the analysis. Okay, so this should be straightforward because you've seen binary classification. Just more labels. And then you want to solve multi-class with binary. So there's this technique proposed by Dieterich and Bakiri, which is pretty nice, actually. It says, suppose you have a binary learning algorithm, then you can solve multi-class classification in the following way. For every, you can create a bunch of binary problems which are distinguishing between a subset of the labels and another subset, right? So the first binary problem is here, and the correct prediction is 1. If the label is 1 or 2, then you're supposed to predict 1, and if it's 3 or 4, you're supposed to predict 0. And then you can create another binary problem, which is here. It's 1 if it's 1 or 3, and you can create another binary problem, which is 1 if it's 1 or 4. And then at classification time, if you want to try to predict what is the right multi-class prediction, you can run each of your binary classifiers, and you can get some predictions. Like, for example, in this case, it's clear that, well, at least it looks pretty clear, that 3 is the right multi-class label to predict. I guess we have at least one error no matter where we are, and the possibilities with one error are 1, 3, or 4, so maybe you randomize over those. And then if you get kind of a very strange, it's 2 errors no matter where you are, right? Or no, I guess it's 1 error here. So the way you do this is you define some set of labels, and the binary training data is just x and indicator function of whether or not the actual label is in the set. And that is how you do it for each of these problems. And then formally, the way that you make the prediction is you just find the closest label vector in a Hamming distance sense of close. So this is a very nice, simple analysis for ECOC, a reductions type analysis. So we're going to use that one classifier trick. So we can take all of these different binary problems here, and we can embed the name of the set into the feature space. Then we can just think about having one binary classifier. Okay, so that's the C is that one binary classifier. And then we're going to think about this ECC of the multi-class distribution as the induced distribution on the one binary classifier. And the claim is that for every number of multi-class labels, there exists a code so that for all binary classifiers and for all multi-class distributions, the multi-class error rate of this decoding process using the binary classifier is bounded by 4 times the multi-class, the binary error rate of this one classifier. All right, so the proof is actually very simple. It's just that there exists a code such that if you have less than 1/4 binary errors, you have no multi-class error. That code exists for every choice of k. So you must have at least 1/4 binary errors to have a multi-class error, and that gives you the ratio of 1 to 4. So this should be somewhat surprising to you, because this is independent of k. Kind of think that when you have more and more multi-class examples, maybe your transform should have some sort of k dependence. There's none here. So that's kind of interesting. So another obvious way to transform from multi-class to binary, you just form a tree. The tree is formed by the predictions. Is it label 1 or 2 or 3 or 4? And then is it 1 or 2 or is it 3 or 4? Right? So that would give you a log k dependence instead of a 4. So one thing that you might want to think about is whether or not this no k dependence is really right. It could be the case that this binary problem becomes more difficult as k gets larger and larger, right? So this term here can be hiding the k dependence rather than having it there. And that might be the case. In fact, I expect that is the case. Okay, so, right, so the proof is simple. Actually, I'll show you a particular matrix which does this, a particular code which does this later. Oh, by the way, this is called a code. And the reason why it's called a code is from coding theory. So you can think about each column as coding the value of the multi-class label. And then you try to decode the closest multi-class label. The intuition for why this is so is if you make these columns very long and you fill them in randomly, then about half the locations they'll disagree for any pair of columns. Since they disagree in half the locations, you have to quarter errors in order to get a confusion about which is the multi-class label. Pretty simple. Okay, so ECOC is something that must be understood because everything else has ECOC in its name. Is it clear? Okay. So there's a difficulty with ECOC, which is maybe not obvious from this initial analysis. So this is an error rate analysis. And if you do a regret analysis, you discover that ECOC is not optimal. In particular, there exists some multi-class distribution such that for every choice of binary classifier and for every code, the error rate of the induced multi-class classifier is not minimal. Even if your binary classifier is perfect for its individual problems, you can't get this to be minimal. It's kind of disturbing. maybe I can even tell you a little bit about why that comes up. We can make, let me tell you a high-level overview of the proof of that theorem. We can make d sub m only have some probability mass on label 2, 3, or 4 given particular value of x, right? So this column goes away. And then if we have a very long, if we have many different binary problems, all of them are equivalent to this binary problem, that binary problem, or that binary problem. Because the decoding process is sort of, the closest in Hamming distance is equivalent when you complement the set. So it's either going to be, well, if it's 0, 0, or 0, then that's meaningless. It doesn't help at all. If it's 1, 1, or 1, it's meaningless. It doesn't help at all. If it's 1, 1, 0, then we can complement that set and get 0, 0, 1. So it says that every binary problem on 3 labels, every code on 3 labels ends up being sort of a weighted sum of these 3 choices here. Okay, so it's a weighted sum of the 3 choices. And then if it's the case that the probability of 2 given x is 0.45, and the probability of 3 given x is 0.25, and the probability of 4 given x is 0.3, then the correct binary prediction for each of these binary classifiers is 0, right? The probability that the labels in the set is 0. So you get zeros everywhere. You get this. And then you just randomize. Or maybe the weighted sum means that you have to pick out one of these. But the point is that the choice you make is arbitrary. Because the choice you make is arbitrary, you can have this distribution kind of shift between the different possibilities in such a way that the classifier just can't pick it out. Okay, so ECOCs are very motivational, but they have a small problem. And now I'll tell you how to fix that problem, at least a way to fix that problem. The fix is to use what we just talked about, this probing technique. So in particular, we're going to make probabilistic predictions rather than making binary predictions. And then instead of decoding with Hamming distance, just trying to get the right numbers of ones and zeros, we're going to decode with L1 distance. And if you don't know what L1 distance is, then it's written out right here. So if we get these predictions for these probabilistic predictions for these binary problems here, then the distance, let's see, I guess 1 would imply that, it's either 1 or 2 always. So 0.91 is 0.09 away from that, and 0.45 away from, and 0.54 away. You sum it up, you get 1.08. You do this for each of the columns, and you get different numbers, and you pick the minimum. The claim is that this fixes the problem. That this small tweak on ECOC fixes the problem theoretically. It also turns out to work. So once again, we grabbed a bunch of data sets, and I think we used a Hadamard matrix for a code. I'll show you what that is later. And you can compare this ECOC test error rate to this probabilistic error correcting output code test error rate. And so this is error rate rather than accuracy, which means small is good, which means that things below the line implies that this is winning. And you see that for a support vector machine, a decision tree, and logistic regression, turns out that the probabilistic error correcting output code is winning on all the data sets. Sometimes it's a tie, but okay, so let's go back here for a minute. This algorithm is clear, right? It's just like ECOC. We have a bunch of binary problems, except now we make probabilistic predictions, and then we decode with L1 loss. We decode to find the smallest L1 distance label. Okay, right, kind of works. It's cool. And now we want to try to analyze it. So we're going to use this one classifier trick again. We're going to embed the choice of the subset and the probability into the name of the classifier. So we'll have one classifier, and we'll define the different probabilistic predictions for the different subsets just by that equivalence there. And we'll let this Peacock, yeah, of D sub m be the distribution induced on that binary classifier. And then we have this Peacock transform theorem, which says that for every number of multi-class labels, there exists a code such that for every classifier and for every multi-class distribution, for every binary classifier and every multi-class distribution, the multi-class error rate minus the minimum multi-class error rate is bounded by 4 times the square root of the binary error rate minus the minimum binary error rate. The square root, by the way, is not great. The square root makes it worse than not having the square root. And so what this says is that the last theorem applying to Peacock does not apply to Peacock. In particular, this can be driven to 0 by a good choice of classifier. That means that this can be driven to 0 by that good choice of classifier. Another thing which is interesting about this is that a lot of people designing individual learning algorithms, like for example support vector machines, have failed to generalize to the multi-class case correctly. And it says that there is a black box technique for generalizing to the multi-class case, which always works for any good binary classification algorithm. And then there are things people keep track of, like consistency and so forth. So this is binary consistency implies multi-class consistency. It's also, so the square root is not great, but because we subtract off this minimum, it says that it might be telling you something pretty non-trivial even when the minimum binary error rate is 0.25, right? So if this is 0.25 and it's 0.25, then this is 0, and it says you must be doing as well as anything. Okay, so that's the theorem. And then, of course, it's traditional to try to prove it. So the way that you prove it is using the Hadamard matrix. Or one way to prove it is using the Hadamard matrix. So a Hadamard matrix has this property that the distance between any 2 columns is half of the number of rows, right? So, yep. Yep. Keep going. Actually, I got fascinated. So there's a recursive definition of the Hadamard matrix. So the way that it works recursively is you take this guy, you stick him here, and here, and here, and then you invert him and stick him here, right? And then you take this guy, put him here, and here, and here, and invert and stick him here. So I went crazy last night. You've got to see this. Right, it has patterns in it. It's a very nice pattern. I think I've actually seen this in rugs. It never repeats. It's pretty cool. We could try for a bigger size. I mean, it's easy in the software. Maybe it takes a little bit longer to load, but my laptop's a little bit slow. But yeah. I'm thinking that maybe I really want a rug like this. Okay, so we have this Hadamard matrix. And the distance between any two columns is a half of the number of rows. So let's let B be the number of rows, the number of binary problems. And the distance between any two code words is B over 2. Exactly B over 2. That equality, by the way, is why we're using Hadamard. It's actually equality. And then the way we analyze this, okay, so we're going to do an analysis assuming that the binary classifiers are perfect first. And then we'll do the imperfect case next. Okay, so assuming that they're perfect, the L1 distance is the binary problems of what probing tells you is the probability of a set containing your label. Right? So probing is estimating the probability that your label is in one set or the other. And you figure out what that set is. The probability, it's probabilistic estimate of that set. And then assuming that this is actually perfect, then that value there is the sum over every label in the set containing the label of the probability of that label. And then there's some sort of fancy switching of sums thing going on here. You say, look, whatever label L we care about, it's going to, by definition, appear in every set that we're measuring the probability of, right? So there's B of those sets, so we have B times the probability of that particular label. And then every other label appears half the time because the distance between the columns is a half. Right? So it appears half the time, which means that B times a half times the sum over the other labels of the probability of that label. And then you just simplify a little bit. This quantity here is 1 minus that quantity. And you get that. So if our classifiers are perfect, this sum turns out to be rows times actual probability plus 1. And then there's this little issue of maybe they're imperfect, right? But it turns out it's pretty easy to analyze. Okay, so you can take the probing analysis and you can kind of throw a square root in on each side. And you can push the square root through the expectation because of distance inequality, and you get this statement. It says that the distance between your prediction and the actual truth is bounded by your binary regret square rooted. And that's essentially where the square root is going to come from. So if B is the number of binary problems, right, so we have this sum here, which is defining how we predict. So the question is, for an adversary, again, we're doing some sort of adversarial analysis. We're saying, suppose an adversary has some budget, shift probabilities by some amount. Or actually, he can cause binary errors. He has some budget of binary errors. And that shifts probabilities by some amount. This is the most efficient way for him to shift the sum. Because the distance that he can shift the sum is going to control the multi-class error rate. So the most efficient way to disturb the sum is to actually have the same disturbance for every element of the sum. And that's because of this square root, right? So in order to get a big disturbance, you have to pay the square of the regret. But so right. That's square root, right? So this says that the size of your disturbance. So the size of your disturbance is like the square root. So the amount that you pay is how far you go out. And the size of the disturbance is how far you go up. So there's some sort of diminishing returns. The further you go out, the less disturbance you actually get. And that says that you're going to disturb each sum the same, each element of the sum the same amount if you're an adversary. Okay, so the most efficient way to disturb the sum by epsilon times the number of binary classifiers is to disturb each individual element by epsilon. Yeah? Yeah, there's always this problem about how you define convex or concave, right? So it's convex in this context, but it could be concave in another context. I guess I think of convex as you can shift things so that all lines go through the origin, but anyways. Yeah, there may be a parity issue. Insert the appropriate thing. That's the graph. The graph is clear. Okay, so what this says is that if we change the L1 sum by b times epsilon, we end up choosing a class which is no more than 4 epsilon worse than the minimum as far as the error rate. And how do we see that? Well, okay, so remember this b times epsilon. And then let's go back a page. And let's look at this. So if we add b times epsilon here, then this factor of 2 means that we're kind of overestimating probability by 2 times epsilon. Right, so this is a b over 2. This is plus b over b times epsilon, which is plus 2 times b epsilon over 2, which means we can think of this as the actual probability plus 2 times epsilon. So we shift our estimate of the probability up by 2 times epsilon. Then we can shift the probability of some other, oh, wait, wrong direction. We shift the probability of the correct thing down by 2 times epsilon. And we shift the probability of the wrong thing up by 2 times epsilon. Then the vote goes the wrong way, and we get the wrong thing. So that we multiply by 2 because we can shift both of these at the same time. Right? So that tells us 4 times epsilon. And then the square root is just this square root. So, oh no, the rug again. Right, so that gives us the theorem. This square root is from probing, applied to that classifier. And the 4 is from kind of shifting things up and down, and also that factor of 2, which comes in from that, from the exact analysis. It's clear in the exact analysis. Okay, so it says that, well, it says the theorem. For every classifier, for every multi-class prediction problem, the multi-class regret is bounded by the 4 times the square root of the binary regret. Then we have Hadamard again. So there's also something cool, which is that you get a bonus round. You can do probabilistic multi-class prediction as well. So maybe that's obvious if we go back and we think about the exact case, because the exact case said that the individual probabilistic predictions work out to that quantity, right? And then we can just invert, right? So we can take our individual problems, multiply by 2, divide by 3, and subtract 1. And that's supposed to be a good probabilistic estimate whenever our binary predictors are accurate. So this, at least, if we tweak things according to this output process, then for every classifier, for every binary classifier, for every multi-class distribution, the squared loss of the true multi-class probability to the predicted multi-class probability is bounded by 4 times our binary regret. We haven't tried to experiment with this at all. Something kind of weird about this, by the way, which is that this formula can go above 1 and below 0. Kind of unfortunate. You can if you clip, meaning you just make sure things are in the interval 0 or 1, the theorem is still valid. Yeah? No. We've been working with imperfect ones as well. Right, so this is perfect, and this is imperfect. Right, so here we're thinking about how we disturb the sum by the largest amount. Let me tell you one other analysis which you should not do for error-correcting output codes. What you should not do is assume that the individual errors are independent and then multiply probabilities in the appropriate way to try to predict the class. And the reason why you should not do that is because it really is the case in practice that these the individual binary problems kind of err in tandem, right? So hard problems are hard for each of the individual binary problems, or at least for a lot of them. And that dependence is there in practice in a big way, so you must take that into account in your analysis. The Peacock? Right. So, did I analyze the running time? No, I did not explicitly. I will tell you, though, that it turns out the running time is actually similar to probing. So you might think that because you run probing many different times, it costs, according to many different runs of probing, which is a little bit expensive. But there's a trick. The trick is, let's go back to the sum. Right. The trick is that this sum can be thought of as an integration over a set of possibilities, or over some set. It can be thought of as an integration. That means that you can just kind of directly approximate the integral. So in some sense, you can think about choosing the set S and the probabilistic threshold P together, right? And maybe even uniformly at random, or maybe according to a grid or whatever. But the point is that this principle that a little information at a lot of places is better than a lot of information at a few places in P, or places in S, holds. And when you use that to compute this integral, the number of runs of the individual learning algorithm actually turns out to be quite similar to the number of runs for if you want to solve probing. So in particular, you could think of an extreme version of this algorithm where we pick a subset, we pick only one P for that subset. We pick a different subset, we pick another P, and we learn. We just learn one individual problem for each P. Then all these predictions will come together at the end and compute that integral. Okay, so that's multi-class classification. And now we have one last one to go, which is custom-statistical classification. This is the penultimate one in a lot of ways because custom-statistical classification can encode essentially anything describable in this way. So custom-statistical classification is defined by some measure on X cross a vector of costs. And we're still trying to find a multi-class classifier, but the way we evaluate our loss is different. So we have our x's and we have our losses, which are drawn from our distribution. And we make our prediction, and then the loss we suffer is just whichever component of the vector was the one. Okay? So this is kind of obviously sufficient to describe anything describable in this way. It would have been in this general format because these L's sub i's have no necessary relationship between them. Yeah?
So is there an obvious difference between this and the first one you showed?
Right. So when K is 2, they're actually the same. So the way to see this is, but it's not quite obvious. So you have the loss of the first choice, you have the loss of the second choice. You can subtract the minimum of these two, and then one of them will be 0. That's the correct choice. The other one will be larger than 0. That's the importance. And you can show that optimizing those two problems is completely equivalent. When you have multiple labels, when you have more than 2, it's not equivalent in general. I should mention one other thing, which is that a lot of people worry about a simplification of this setting. They also call constant classification, where you have a matrix which is kind of So the matrix is something like labels cross labels. So maybe it's 1, 2, 3. 1, 2, 3. And then maybe you fill in cost 0 if you predict. This is the truth, and that's what you predict, and then maybe you fill in some numbers here. 5, and 10, and 11, and 7, 4, 3, right? So this is a simplification. This is a strictly simpler setting. And the reason why it's simpler is, first of all, for any individual example, you only care about one row, right? And then we can express that row in these losses. It just happens to be the case that those losses are always the same whenever a particular correct answer comes up. All right, so sensitive recursion conflict codes, or Peacock. So going to reduce cost-sensitive classification to importance-weighted classification. So it's all the way to that first slightly non-trivial problem I talked about. And once again, we're going to have a coding matrix. So just think about the same coding matrix as before. How do we do it? So this is the training algorithm. You have your set of cost-sensitive examples input, and you have your importance-weighted learning algorithm input. And then for each subset of the matrix, we're going to, and for each example, we're going to think about the sum of the costs and the sum of the costs inside of the subset. And then we're going to pick a random threshold in the interval 0 to 1. And we're going to define an importance-weighted data set out of the cost-sensitive data set, where the label is the sum of costs in the subset greater than t times the total sum of costs. And the importance is how far that decision is from 0. Oh, there's a mistake. No, this should be a C. You want to return the classifiers that you learned. So this is using the trick that I mentioned to you. What's your name? Yeah. This is the same as the trick for Peacock. So we have a subset, and we just pick one random t. Maybe in practice we'll actually use grids or something, but we're just going to have, it's the same general intuition. We're just going to have some integral we're going to compute, and this is the way that we compute the integral in sort of a Monte Carlo form. So I would love to tell you that I've done a zillion experiments and this works great. But the truth is I've done 0 experiments so far. And I will leave the motivation to the fact, the empirical motivation to the fact that this style of analysis has often been useful. So now there's this question about how we actually do a prediction. So we have our binary classifiers, we have our example which comes in, and then we compute the expectation over the subset and the expectation over T, this is the integral, of the binary prediction when y is in S, or 1 minus the binary prediction when y is not in S. And then we multiply by 2 and subtract 1. Well, I guess these don't really affect the minimum. Ignore that. Ignore that. But the reason why you want to do the 2 and the minus 1 is you're trying to estimate the relative cost of the subset. We'll get to that later. But we compute the minimum, and we predict according to whatever the minimum is. So maybe there's an R minimum. Okay, so some sort of prediction algorithm. The question is, does it work? And the answer is, yeah, we can prove a nice theorem that says that this should work. So once again, we use this one classifier trick. We take all of our data sets, all of our importance weighted data sets, and we add in the name of the data set to the feature space, and then we get some super data set. And then we train on this super data set. And then we can just get back these individual classifiers by putting in the appropriate name. And then we can prove this theorem, which says that for every number of labels, there's a code just that for every binary classifier, for every cost-sensitive data set, the cost-sensitive loss of the cost-sensitive classifier, or the multi-class classifier defined by that binary classifier in the decoding process, minus the minimum, is bounded by 4 times the square root. This is the binary loss on that classifier C. This is the minimum binary loss. And then we multiply by the sum of the costs. Do you know that there had to be some term like this for the same reason there had to be some expected importance term for importance weighted classification? Now, the fact that it's the sum of costs, that's a bit unfortunate. You would hope that it would be smaller than the sum. So in particular, if you took multi-class classification and you embed it into cost classification, that sum is going to be k minus 1. Right? So it's not as ideal as Peacock transform for multi-class classification. Nevertheless, it's giving us something, right? It says that if we optimize our binary error rate, then we optimize our cost-sensitive loss. And maybe that's useful sometimes. Okay, are there any questions about this? I'm going to spare you the full proof, but I'll tell you roughly how it works. So the proof is actually very similar to Peacock. The inner part of that integral, just fix S and fix Y. Just expectation fix T of that quantity. And you can prove that this is much like estimating the probability. You can prove that this equals, when the classifiers are optimal, this gives you the expected loss of the subset divided by the expected sum of losses. It kind of makes sense. So let me tell you something which sort of motivates this. We can take all the costs, we can rescale them so they sum to 1, right? And then we have a bunch of numbers which are greater than or equal to 0 and which sum to 1, which is much like a probability, right? So we're sort of getting the probability of the subset. Except instead of probability, it's the relative cost. And then we can throw in this expectation over subsets. And we can do the same. This is really a sum. That's really a sum. So we can do some sort of switching of sums thing again. And we get that this expectation over subset of this is the expected loss of some particular label divided by the sum of expected losses, the sum of losses, plus 1 divided by 2. So if you think back to the Peacock analysis, which said we get the probability plus 1 divided by 2 times the number of rows. And the reason why we don't have a number of rows is because we're actually taking expectation of the rows here. And then we go through the same process of saying, what could an adversary do? And the optimal strategy for an adversary is the same as for Peacock. So he wants to kind of induce losses all on the same side of the actual expected loss for each individual sum, for each individual subset. And then, since the cost of varying is linear in how far that t is from the relative, let's go back here. One more. Since the importance is linear in how far this differs from that, we're going to want to err as near to the point where this equals that as possible if we're an adversary on a budget. So you get the same little triangle, and then you get the same integral, and then you get the same square root. All right, so something going linearly means that the integral is quadratic, and that gives you the analysis. Okay, so that's this theorem. It says that, at least theoretically, we can try to solve everything kind of phrasable as a classification-like problem using a binary classifier. Even if that's handy sometimes. Right. So we have bonus rounds. So we can modify our prediction using that multiplication by 2 and subtraction of 1 to estimate the relative cost. So this says that we're getting everything up to a normalization term. So we can actually estimate the relative cost of one label versus other labels. So it can kind of tell us how close we are to switching over or whatever. And that's bounded by, again, the binary threat. There's no square root because we have a square here. And the 4, you might expect this to be a 16 because we squared everything, but it's a 4 because we don't have to pay because we can have errors in both directions. Right, and there's a way actually to interpolate between this Peacock and Seacock. So I told you that if you embed multiclass into classification, this multiplication by the expected importance is k minus 1. That's bad. But it turns out that if you embed it and you make Seacock run only for the non-trivial t's, it turns out that if your subsets here might be, your subsets S might be half of your labels, right? So it says that the dynamic range of L sub S is going to be something like n minus 1 over 2 to n plus 1 over 2, or n is b plus 1 over 2 to b minus 1 over 2, or b is the number of rows. So if you fix your t's to be in that smaller dynamic range, you end up getting exactly the Peacock analysis. Okay, this is all getting mathematical and esoteric and so forth. So let's stop. Oh, not quite. So there are some things to think about. All right, experiments. Good to know how well this works. Oh, there's this cool thing about codes. So Shannon pointed out that if you pick randomly from subsets, then you end up with a good code after just O of log k choices. There's lots of work de-randomizing that, but theoretically at least, it's possible to get by with only O of log k, only order log of the number of labels binary classifiers. Or R1 if you do the squashing technique. Okay, so that's it for the real content. And then I wanted to show you a couple pretty pictures before we finish. So I showed you a few reductions. So this binary classification here is importance weighted classification. And I guess when I drew this picture, I was thinking about this probing one is going directly to classification, but it's really composing. Maybe the arrow should actually be going to importance weighted classification, right? So it's a question about if you compose two reductions, you get one reduction, right? The analysis has to work out that way. So if you compose costing and probing, you get something that reduces directly to classification. But maybe you don't want to do that, in which case the arrow should actually be going to here. And then we have this technique for doing multi-class classification using class probability estimation. So that's Peacock. Then we have this technique which does cost-sensitive classification with importance weighted classification. That's Seacock. And then everything. I guess the blue arrows here mean defaults, right? So all the hard work is on the black arrows. And it's kind of a trivial way to embed everything according to the blue arrows. So we can take any bounded loss classification problem and embed it into cost-sensitive classification and vice versa. And then, right, there's some work here, actually. And that arrow is not entirely satisfying. But there is something. Reinforcement learning is actually a pretty hard problem. And then you can embed various things into all bounded loss classification problems. So are there questions about this graph? It's a nice, pretty picture, I guess. Okay, so one thing that I wonder about, well, in addition to trying to precisely define this arrow more thoroughly, one thing that I worry about is other learning problems which are not here. All right, so that's that graph. And then you can actually also draw a graph for just error limiting reductions, right? So these are less desirable, but the actual analysis that we get is tighter because there's none of the square root garbage running around. And maybe that's important sometimes. So this is multi-class classification here, and there's sort of three very common methods for reducing multi-class to binary. One of them is ECOC. One of them is this tree reduction, where we just say, the first problem is it the label 1 or 2 or 3 or 4? And then is it 1 or 2, or is it 3 or 4? And this is 1 against all, which I explained to you. This is weighted 1 against all, which I showed you a graph at the beginning about. There's boosting, which you can think about as a reduction. There's this subset classification. So weighted 1 against all can actually be used for subset classification as well. So subset classification is instead of having one right choice, you might have two right choices. So it might be 2 out of k, or it might be or 2 out of L, I guess, or 3. You might have 3 right choices out of 5, or something like that, right? So it's not quite as general as custom classification, but it's somewhere in between. And you can use weighted one install for that. And then there's this weighted all pairs reduction, which reduces custom classification to importance weighted classification, so that the binary array moving through costing, and down here, found the cost-sensitive loss by 2 times the binary array times the sum of the costs. And then here's this arrow to reinforcement learning again, but some more work is required there. Yes?
Yeah, it's probably a stupid question, but where does 1 against 1 classification fit in?
1 against 1?
Yeah.
Binary classification?
No, reducing a multi-class problem.
Ah, right. All pairs. That's what it's called, I think.
Okay.
All right, so there's another one which I left out here, which is all pairs. So that would be going from multi-class to binary. And I guess that's half of this name. It's this part. So that might give you some idea of how this works. So the way that all pairs works is you take every pair of classes and you make a classifier which is just this class or that class. And the way that you create the training set from the original set is you just kind of filter on this class or that class. Right? All right, so it turns out that all pairs has a terrible analysis in this sense. Well, it's as bad as 1 against all, and you do a lot more work. The reason why it has terrible analysis, so the way that you decode for all pairs is you take every classifier and you evaluate it, and then you just see, does this label agree with the predictions the most, or is that one, or is that one, or is that one? So you evaluate all k times k plus 1 over 2 classifiers. And the problem is that, the problem is you just don't get any analysis any better than this. It's kind of unfortunate. There's another problem, which is, so you can take these analyses, and you can actually prove, so for all the analysis that I talked about today, you can say, if it's the case that my data is actually drawn from this distribution that will be tested on, then the method of transforming samples that I used transformed things into the correct distribution. And that's not true about all pairs. The reason it's easy to see this because when you train for all pairs, you're only training on samples which are conditioned on being in class I or class J. But when you test, your examples might be any other class, right? And that means that an adversary is kind of free to do anything he wants, which is part of the whole reason why you get a bad analysis. Okay, so so one last thing is I really like boosting, and you should definitely come to Robert Shapiri's tutorial. Which I think is on Friday, not this Friday, but the one after that. So boosting is like reduction, but it's also unlike this because it's not trying to solve a bunch of different kinds of classification problems. It's actually trying to solve one classification problem. And some clever technique of sort of reusing the learning algorithm over and over again to try to compensate for the weaknesses of the previous runs. Okay, so this is the end. You should understand that the study of these reductions, this sort of formal study that I showed you, is relatively new. Which means that what exactly we can do and can't do is not entirely well defined yet. It also means that if you wanted to work on it, you could easily do that. Right now, what I'm working on is trying to produce some sort of coherent code base so that you can easily use these things, and some sort of coherent tutorial, like in paper form, so that you can read everything that I presented now. All right, so thanks. Are there any questions? Yeah? Are there lower bounds? That's a really good question. So these blue arrows, composed with the black arrows, imply a lower bound of sorts. It's actually it's a little bit tricky talking about lower bounds because boosting is around. And this boosting, well, you'll see later, implies that you can keep on improving as long as your original classifier, as long as the classifiers you learn are doing something useful. But if you don't allow some sort of adaptive feedback, you can state lower bounds. You can say that it's impossible to go from multi-class classification to binary classification with a transform of less than epsilon, right? Because you can embed binary classification into multi-class classification, and, well, do any better. There's actually, the proof of that is actually more subtle than I'm letting on. There's some sort of describing of hypercubes and so forth and talking about cuts through the hypercubes, but there are lower bounds of this sort when you don't allow adaptation. When you allow adaptation, everything is sort of out the window. And there are significant gaps between the lower bounds that you get and the upper bounds that we get. So it may be that it's possible to improve the 4 epsilon. Anything else? Okay, I think we'll take about a 20-minute break, and then I think Steve Smale is going to talk to us.